issues in terms of doing that, but now it's working, and people are starting to file into the meeting. So I want to go ahead and introduce you.
Well, that's fine. We can wait for a few minutes if you want.
I think go ahead and set up your slides. I'm going to make you a co-host, so you should be able to do that. Okay, you should be able to share your slides, and I'll get my little materials ready for your introduction.
Let me see. Yeah, I can share my screen.
Okay, good. Go ahead and do that, and people are going to keep filing in as we go here. So I want to welcome everyone to our last seminar series, installment of our biostatistics seminar series for this semester. I'm sorry for the confusion we had with the link. We tried it 15 minutes before and it just stopped working. I'm not sure what was going on, but here we are. So I want to welcome you all to and our special guest, Dr. P.Song from the University of Michigan. I'll do a very short introduction and we'll get started by 12:15. So Peter is a professor, full professor in the Department of Biostatistics at the University of Michigan School of Public Health. He and I go back many years, and he's actually friends with a few of us here in the division. We have sort of crossover Canadian roots. He got his PhD at the University of British Columbia in the Department of Statistics in 1996. And then he spent a number of years on faculty in the Department of Mathematics and Statistics at York University in Toronto, and then moved to the University of Waterloo in their Statistics and Actuarial Sciences Department till 2007. And then from 2008 onwards, he has been at the University of Michigan. He has a very, very active research program in many, many areas. And so I'll read you a little blurb about him. So he develops innovative statistical methods for the design and analysis of biomedical studies and its application to medical and public health sciences. His specific fields of methodologic research include things like data integration, data harmonization, high dimensional data analysis, longitudinal data analysis, missing data, spatiotemporal analysis, bioinformatics, and genetics. He's got deep collaborations in areas like nephrology, pediatrics, environmental health, nutritional sciences. The other thing he's been doing a fair amount of work on COVID modeling, and some of his compartment models that he and his group have developed have been very actively used around the world, specifically in places like India in terms of informing public health decision making. So he's got broad interests, broad range of expertise, and it's a real pleasure to have him here as our guest speaker. So today he's going to speak about mediation pathway analysis, and I will hand it over to Peter and not take any more time. Welcome, Peter.
Thank you, Sanyo, for the introduction. I'm sorry for the technical difficulty, and from time to time we have this issue when we have this sort of virtual meeting, and finally we figured out. And so anyway, so I have about 40 minutes to go over my slides, and so if you have any questions, just stop me, ask me a question, unmute your audio and ask questions. So I like to talk a little bit some of the work I have been doing in the past like 5-6 years or so, because I've been involved a lot of this cohort study, observational study, where the people are interested in solving some of this mediation analysis, either in the grant proposal or in the their applied papers. So I some kind of exposure to this topic, and when I try to find out a little bit deeper in this sort of area, I found that there are a lot of challenging problems, methodological challenges that probably this community has not paid much attention to. I think that maybe this is the area that deserves more attention to develop new statistical methods. Okay, I will cover some of this. And so because that this sort of work has been sort of for years, that so we have several grants that related to this kind of research work. Okay, let me just move to next slides. So basically, I would like to cover two problems if I have time. And one problem is about the hypothesis testing for mediation effect. and that this seems to me is a still open problem that is not fully resolved yet. I will give you a little bit the insight why this is a problem that has not been solved in this statistic. I mean, people have used software packages and all sorts of things that so far, I think there's still the issue that we need to really overcome. And the next part, I'd like to cover a little bit some of the recent work we're working on for this high-dimensional mediators, and how could we come up with a little bit more rigorous way to handling, high-dimensional mediators. Okay, of course that when you work with those applied scientists, that they always start with this sort of three variable directed acyclic graph, or we call it DAG, right? So that you have exposure S, could be exposure to lead or some kind of environment sort of toxicants, then you have a mediator, could be methylation, could be metabolized, or could be some of social determinants, whatever that would be suitable in their actually applied problems. In environmental health sciences, in medical sciences, mediators are frequently raised up in their in the research or their questions they like to answer, so that you have your outcome, right? So just for simplicity, that I assume that all three variables follow normal distribution, so that I can really put this problem into this classical structure equation modeling approach. So of course that in observational study, that you have potential confounding factor. So here I do not talk about propensity score. I'm just saying doing this very classical sort of the covariate-based confounding adjustment. So of course that when you have this a DAG, the DAG, right? So this is a this triangle relationship from exposure to M, the mediator to outcome, and then the exposure to the outcome directly. Any questions? So this is actually a very classical, the graphic representation of this relationship of these three variables under this so-called the DAG sort of topology. That based on this DAG, that you can decompose this joint distribution of outcome and mediator and exposure conditional on the confounding factors into this sort of the product of three distributions. Then for the first one, then you can formulate this regression model, and for the second factor in this decomposition, you can formulate another regression model, and that this is basically the formulation of the classic structure equation model. And for simplicity here, I just assume that all the error distributions are normally distributed. So there are two key parameters of interest in this formulation. One is the alpha, which describe this relationship from the exposure to mediator, and another one is beta. That's the the key parameter that describes how M affects the Y, right? So that's basically what I have. So that of course in the counterfactual framework, that people trying to interpret alpha and beta in some kind of sense of causality, and I will review that later. But overall, that people like to quantify or assess or evaluate the mediation effect of S on Y through a mediator M, which is basically a product of two parameter alpha times beta under this structure. So if you write I want to make two quick comments that if you write this structure equation model in this way, that you can say that S and Y, and based on the classical structural equation model, you basically can write this in such a way is obviously that these confounding factors are affecting the mean of this three variables. And the this alpha, beta, and tau, those the parameters in the this DAG, okay? So the tau, tau is the effect from S to Y in the equation here. And then you can see that effectively these three parameters are actually associated with the covariance of these three parameters. So although that, a lot of people are doing this sort of extension from the structure equation model from normally distributed variables to non-normal distributed variable, for example, survival or some Y is outcome, like binary outcome, like for logistic regression. They mostly trying to extend from this conditional equations, the comarginal regression models, where they probably will lose this kind of a nice interpretation that those parameters that we were really interested in the structure equation model are actually the parameters related to the modeling of the covariance structure, which is somewhat aligned with the approach of we see in the literature utilizing covariance to model certain network topology. And this is in my view, is this parallels the view of causality. That's something very important comment to notice that under this kind of formulation, confounding factors and these parameters in the relationship of the three variable play different roles. Once in the first moment of the distribution, the other set of parameters are actually affecting the second moment of distribution. Of course, that we have learned that in the counterfactual framework, people trying to interpret the meaning of this directionality in the relationship of the three variables, so that we have the so-called natural direct effect, NED, and natural indirect, NIE. So that, people have, work a lot of this sort of understanding or interpretation of those parameters under this kind of counterfactual framework. So for the natural direct effect is that you, look at the average effect under different conditions of your exposure when mediator is fixed. So basically, if you block the path from S to Y via mediator, so mediator is fixed. You look at how this average change will be when you change your exposure from S1 to S0. So natural indirect effect, NIE, is basically the fact that of your exposure on the Y via the mediator. Okay, so in this case, you basically just fix this direct effect, and you have this pass from S to M and M to Y. Okay, so that you have this total effect, right? So total effect is the sum of this. And under this sort of this linear normal structure equation model, we can easily prove that the NDE, the natural direct effect, is tau times the change of the exposure, and natural indirect effect is the alpha times beta, times the change of exposure. So if you really want to look at this sort of the natural indirect effect, or namely, sometimes people call this mediation effect, you're really looking at the product of alpha times beta. So this product of alpha and beta gives you the interpretation of mediation effect. Okay, so in reality, of course, in application, a lot of time we are thinking about how we can test whether or not there is a mediation effect, right? So you basically want to test whether or not alpha beta equal to 0. So this is a very well-defined problem if you want to really test for the hypothesis of existence of mediation effect. However, this non-hypothesis is somewhat complicated because it gives rise to three scenarios. This alpha times beta equal to 0 can be the case of alpha is 0, beta is null. or alpha is 0 and beta, alpha is not 0, beta is 0, or both are 0. Okay, so we call this composite of 3 cases, okay, or composite of null hypothesis. Of course, the alternative hypothesis, both alpha beta are not 0, so that you can establish the path from S to Y, okay? So the working this kind of this problem for a few years, I found that many of the existing methods developed in literature can work for case 1 and case 2, but fail to work for case 3, because the case 3 that the parameters like alpha equal to beta, they actually have different types of distributions. So case 1, case 2 have one type of distribution, and case 3 has another type of distribution. So you cannot use the one distribution to really make a type 1 error control. That's actually the difficulty. So the famous one, of course, is the product coefficient POC. We call this Sobus test. So if you have the estimate of alpha and estimate beta, then Sobus test, which is very, very well known in this community, is really just doing the product of these 2 estimates, right, and standardized by the variance of this estimator. And then you can prove that the convergence to standard normal distribution using the first order delta method. And then they have this all calculation. And this proof is under situation of case 1 and case 2, not case 3. So if you have case 3 like this asymptotic distribution is it still have the asymptotic normal, but the variance is different. Okay, so that this is challenge, because in reality you don't know which case is the true case, right? And so you will have different types of distribution, and then you don't know which distribution to use, because you don't know actually the underlying truth of this noun, right? So that another popular method is the max P test, or joint significant test, where you calculate the P value respectively, and then you try to take the maximum of the 2 P values and trying to use a significant level, omega, to control the type 1 error or make a decision of rejection. However, if you do a little bit of asymptotics, then you find that this only works when in the case 1 and case 2, if you have this case 3, and the type 1 error is actually controlled by the square of the omega rather than omega itself. So basically that you will end up with somewhat very conservative type 1 error control, okay? So people also trying to use, the bootstrap method to overcome this, like the existing software package, the one we use quite popular, the mediation R package that we use, right? So they implement bootstrap method to hopefully to generate some finite sample distribution to, hopefully overcome that issue. But the problem here is that the bootstrap can fail in the case of alpha and beta equal to 0 due to the non-regularity issues. So here is a very simple simulation to show that. Okay, so let's consider Sobus test, product coefficient test. So that like you could do like we did this very simple simulation. You have this typical case of alpha equal 0.05. You replicate the simulation 2,000 times, and then you have sample size 200 and 500. And then, if you have the data generated from this, then the type 1 errors are, reasonably controlled. But if you use this sort of bootstrap method, and in the case number 3, right? So none of them really give you the size alpha test, is overly conservative. So this is really a challenge, because you don't know if in reality you have this as, the true case, or is this actually, the true none. Okay, so that because of the composition, right? As I said that, this alpha times beta equal to 0 is associated with one of these three cases. You don't know which case is the true case. If you happen to have this case 3, where the both paths are broken, then if you use this R package to do the bootstrap thing, you still have very, very conservative, even though you generate the the finite sample distribution to determine the decision rule, but they still have very conservative things. So this is well known actually in the literature. I'm just trying to give a little bit numerical evidence to illustrate that the magnitude of this conservativeness in it. So the consequences, of course, is that you lose power because you are not really utilize the allowed sort of the size of error that in the test. You're over protection of your, so you're too unfriendly to type 1 error. So what are you going to do to overcome this? So recently we're trying to solve this problem, and we use this sort of adaptive bootstrap method, A/B test. So what we're trying to solve here is that we introduce this indicator function. So the indicator function would somehow help us to learn which case actually is the case, so that we introduce this sort of the indicator function, and of course that when this this equal to 1, that basically means that this you are in the case number 3, alpha equal to 0, beta equal to 0. So that we try to use the idea from this adaptive bootstrap published in the JASA. That's very, very interesting approach that help us to learn what the situations in the boundary of your parameter space. So by introducing this sort of the product indicator function, that we can, to some extent, to learn what possible underlying truth would be. Okay, so that you have the tuning parameter there to decide as part of the learning of this. Okay. So adaptive bootstrap sample is the case that we need to use this approach to actually estimate this indicator function. Okay, this indicator function is somewhat like a classifier, right? It's a clustering sort of operator that helps us to determine which case might be, right, according to the data. Okay, so that you have the product of coefficient test, and at the same time you have extra term, that's the term that is under the situation of both alpha and beta equal to 0. But you learn this sort of the indicator through this adaptive bootstrap. Okay. So we prove this bootstrap consistency under some rate of this tuning parameter. Now here is the simulation of the result that we trying to understand the performance of this. So you can so this the Brownish plus is the method from the current R package mediation based on bootstrap method. Okay, so so I want to have your attention to this the method of this A/B method, the first one, the circle thing, right? You can see that this is the case of alpha equal to 0, beta is not. The middle one is alpha is not, but beta equal to 0. And the third case is both alpha equal to beta equal to 0. You can see that our method, this POC AB method, is really, really on the line of this diagonal line. If you use the R package, which is the CM, causal mediation analysis, that you can see that in the first 2 cases are fine. But in the third case, when both alpha equal to 0, then it has this sort of very conservative sort of the distribution, and the method called MT compt. This is the one proposed by Dr. Huang, and this method works fine in the third case, but not in the first two cases where this MT method are having this inflate type 1 error. So same phenomenon for this max P test, joint significant test. The bootstrap method is really, really conservative. And so, but our method, using this adaptive bootstrap works pretty nicely in the control of the type 1 error, so that you end up with size alpha test rather than a conservative test. So then if you do this power calculation, okay, you can see that I want to have your attention to this, this sort of the square. This is the one we proposed, okay. So this one, the star one, right, is the one that the MP, which has the inflate type 1 error. No wonder that you overspend the type 1 error so that you get a better power. That's understandable, but this is not the test that gives you the good control of type 1 error, so it should not be used in practice. But the one that they are either conservative or the type 1 error control. So the one that we have here, the square, is the adaptive bootstrap, is the has the highest power in comparison to other. And this one, like the Brutish, the one from the R package mediation, so has a lower power, right? So what I'm trying to see here is that because the conservativeness due to this difficulty of not knowing which case is actually the underlying choose, if you use one distribution to control type 1 error, you would end up with this conservative situation that you lose power. That's really very clear to see. Okay, I mean, this is a very sort of simple story about what we are trying to achieve. And in terms of all the technical details, this paper is under revision for GRCSB. So if you are interested in these technical details, I can send you the manuscript. But what I'm trying to say here is that, this mediation analysis is widely used in practice, but this conservativeness is a challenge because, we do this applied statistic, we really want to, have a right sort of the sample size of power in the real analysis. But the current solutions are not providing very desirable power because of the the difficulty of the technical sort of aspect of this mediation analysis, as I described. Okay, so I think that this is the case that about one-dimensional sort of mediation analysis. We already sort of experienced quite a bit the difficulty. Okay, so this problem can become a lot more complex when you have multidimensional or even high-dimensional mediators. But nowadays, we're doing the methylation analysis, metabolomics, or they all think that you have cluster of metabolites where you have some of the CpG size as a set of these mediators in the mediation analysis. So we have to face this situation of, dealing with high-dimensional mediator or multi-dimensional mediator. So how we're going to deal with that, even the one-dimensional case, we already see a lot of challenge, and how do we do that? So in the recent years, we're trying to find some way to solve this, or different ways to solve this problem. Because what you have observed so far is really that you need to do two things simultaneously. One is do clustering. You somehow need to, classify the parameter configuration into different groups, because different types of the parameter configuration associated with different type of distribution. Or, and in previous work, what the solution we propose is trying to use indicator function, sort of like a clustering operator, to sort of split the cases, case 1, case 2 versus case 3. Now, if you have a lot of mediators, how do you develop that kind of the clustering operator in the same time of doing hypothesis testing or estimation? So that's the problem we're trying to solve. So our progress is very slow, but I want to share some of this recent work, ongoing work that we trying to do to attack this problem. Okay. So for simplicity, suppose I don't have any sort of confounding factors, just for simplicity. Okay. Then I have one-dimensional exposure and I have a one-dimensional outcome, but I have a p-dimensional mediator that are correlated. Okay. So that you back to this structure equation model, then you have a p-dimensional multi-regression model for mediators, and you have one-dimensional regression model with p-dimensional predictors, right? From your mediator. So p could go to infinity if you think about high-dimensional case. Okay. So the first objective we're trying to solve in this sort of research is to cluster pathway into 4 groups by labeling mediation effects. So we want to sort of identify a path with both alpha and beta not equal to 0. Okay, so this is the case where you have this complete bridge from your exposure S to Y, okay? So all the other 3 cases have this broken edges, right? Either the broken edge occurs from mediator to outcome, or it occurs from your exposure to mediator, or both edges are broken. So that your parameter can be classified to the 4 groups, but you don't know what is the truth, right? Now you have many different situations. How do you tell which case is which, right? So that's really something a little bit complex, okay? In addition to this sort of labeling task, we also want to see that let's just do this estimation of those parameters in the same time of the labeling. Okay, that's something I like to talk a little bit. And also, of course, you want to do hypothesis testing, right? So, but the inference part is even more challenging. So it's not in my talk today. Okay. So in the talk today, I want to focus on the a statistical method that can achieve object 1 and 2 simultaneously. So here is what we trying to sort of set up this problem. So first we write this problem as a multi-dimensional model. Here that remember that M is p-dimensional. Okay, so that you can write this vectorization the M p-dimensional mediator in this way. And this is just a simple algebra, the way of doing. So I want to introduce some notation here that this vector is denoted by V, and this matrix is denoted by D, and this is denoted by the parameter. Okay, so here that you have this 2p plus 1 dimensional parameter. Okay, so the alpha is p-dimensional because you have p-dimensional mediator. Okay, the beta also is p-dimensional because you have p-dimensional mediator. Okay, so one is outcome, another one is predictor. But anyway, you have 2p plus 1 dimensional. Okay. So of course that that if you think about this number of groups that we're talking about, right? So you would have the number of cluster 4 or less. Okay, that's something you're trying to see. So what we're trying to solve here is this sort of mixed integer programming or MIP formulation. So what we're trying to do here is trying to turn this clustering problem to an estimation problem. Okay. So instead of we say cluster the alpha times beta into one of the 4 groups, we say, well, can we estimate those labels? Okay, so that's what we're trying to approach. So I introduce this sort of parameters. There are labels of the groups. Okay, so there are integer parameters because we want to put these labels as parameters, but labels is either 0, 1. Okay, so those are integer parameters. Okay, so we introduce this kind of latent or unknown parameters as labeling for the purpose of labeling. Okay, so but of course this labeling parameters have to be constrained in order to really reflect that actually the group, the meaning of the labels that you want to estimate. For example, for the first eta j alpha, right? If alpha j is not 0, so basically the bridge from the edge from S to M is not broken. Okay. If this from S to M is not broken, so alpha j is not 0, then eta j alpha has to be 0. Oh, the eta j this labeling has to be 1. So basically, I use the 1, okay, because this can only take 0, 1, okay, as the parameter values. So I just say if this is, the bridge, the edge is not broken, then the parameter has to be 1. In order to satisfy this constraint, so on and so forth. Okay, so you introduce this sort of labelings, and also you could control the sparsity. So how many double edges, a pair of edges that are both non-zero, okay, or one of them is 0. So you could introduce the sparse penalties to penalize number of the sort of the mediation effects, namely both alpha, beta are not 0, or one of them is not 0. So you could penalize them in this way. Okay, so this becomes a mixed integer programming problem where you have your theta parameters, the model parameters that are really just continuous parameters, right? Then you have your labeling parameters or group sort of membership parameters that are integer parameters. You need to solve this sort of optimization problem, simultaneously to estimate not only model parameters but also the labeling parameters. So at the end, you can imagine that you can basically use the estimated labels to really split the parameter into different groups. So that's exactly what we're trying to achieve here. So you have this different sort of parameters that the labeling parameter that will tell you that which type of this sort of situations that this mediator is involved. Is really the mediator has both edges broken where both edges are fine, and so you have this estimated the labeling parameters out of it. Okay. So if you want to solve a low dimensional problem, like say 200, 100, 200, then you can use this commercial software package, Groovy. Okay. So this is the software package I use quite a bit in the optimization problem for organ exchange program, because I work with Jack Kofflish in the past 10 years or so, founded by NIH to study some optimal allocation strategies to exchange, so to allocate organ, like kidney organ, in the organ transplantation program. And so now I know this Groovy, and so, okay, let's solve this problem use Groovy, right? So that's but we found that immediately that this Groovy can only work for low dimensional case. If you really want to work on high dimensional mediator, you need to do something a little bit new. So that's why recent years, we proposed something called Apollo algorithm to solve this high dimensional case. So what is the Apollo the algorithm? So it's alternating penalization operator for error zero loss optimization. So what we're trying to see here is to design a search algorithm to mimic the moon landing procedure. So what you're trying to do here is you have the co-star and use a very fast algorithm to update your co-star value and to some warm star value, right? Which basically is you send your spaceship somewhere close to the orbit of the moon. So then in the second step, that you're trying to have a little finer algorithm that can help you to really land on this spot of the moon that you like to do. So in the second stage, you need different technique to really do a finer sort of procedure for the search in the space of lattice, right? So that's the design is very, very similar to the moon landing program. So first you send whatever the flying object to somewhere very close to the place like you want to land. Then you try to do a little bit detailed planning or search to actually find a spot to land. So we call this Apollo algorithm that we developed. So how do you do this? So for the updating from co-star to warm star, so basically you send the flying object from Earth to moon through a very fast algorithm. We do this sort of upper bound search using a quadratic sort of approximation. This is something that you can do it very quickly. Okay, do this curved tangent approximation. So this, of course, that this is a little bit different from traditional one, because remember here that we have integer parameters in this space to search. Okay, a little more challenge. So now for the landing part, how do you do this landing part? So here you use lower bound search using this cutting plane algorithm. So you do this, so the cutting plan to do that. For example, you have 1 point here and 1 point here, then use two hyperplane and tangent plan, then you end up with 1 point here that could give you an update here. After you get an update here, then you get another hyperplane and you get another point that will be getting a number here. So then you gradually could move into the minimum that you like to achieve. So the cutting plan is slower than this upper bound search, the quadratic sort of tangent curve. But it gives you, it takes a bit of time, but if you have very, very nice warm starting value, namely the value is very close to the position you like to land, then you can get a little bit computational sort of cost to search a finer position you like to achieve. Okay, so that's exactly what we're trying to implement in the Apollo algorithm. And so far, based on this algorithm, we can push the dimension to 50,000. Okay, that's the 50,000 mediators to achieve this simultaneous operation of clustering and estimation. Okay, so that's something we did. In terms of the theoretical property, that we also trying to understand the at which level this problem is solvable. Of course, that it sounds too good that you need some, this is not free lunch, of course, that it really depends on how complex the problem would be. And so not every problem is solvable in this context. So we sort of trying to understand that how to quantify the feasibility that this problem is solvable. So we first define this oracle solution. The oracle solution is the solution that under which you knew these two subgroup labels. Suppose you know the two subgroup labels. You're trying to do this sort of least square estimation, which is relatively simple, right? So that should be doable. So this is the gold standard that we would use as the reference to quantify how likely that our solution from MIO, this mixture integer optimization solution, can be close to the one that you obtained under the true label subgroup labels. So here is the theoretical result. So we work out the finite bound. Okay, so basically this is probability that this MIO, the solution that we propose by the Apollo algorithm, right, is not going to recover the this Oracle solution. What's the chance of that? Okay, this chance will be equal to this. And the most important term, of course, here is this difference. If this difference is positive, then this upper bound will go to 0 because there's a negative when n goes to infinity. So what is this? Okay, C minimum basically is a metric proposed by people in this field of IMO field that measures the easiness of a MIO problem for feature selection. The bigger the C minimum value, the easier for this MIO solution. Apparently that you cannot solve every MIO problem unconditionally. You have to have the situation, the problem is solvable. Then how do you quantify this, whether or not this problem is solvable? And this C minimum is the metric proposed in operational research to quantify that. So we find this that this is has to be as easy as this level. So log 2p over n times p. Okay, this order is the minimum easiness that required for the MIO problem to get a solution. Okay, so finally, I don't have much time. I give you a little bit simulation result and to show you that how this works. Okay, so we did a lot of simulation to test and examine the feasibility and computing performance of the algorithm. And okay, so we could have continuous exposure, we can have binary exposure, and we have the sort of correlated mediators. We use exchangeable correlation or compound symmetry correlation with correlation 0.5. We vary this rho, and so we have, different values of the alpha and beta. Here we particularly have either 0 or 0.2. Okay, 0.2 is relatively low value, but we're trying to see how our algorithm will work for this sort of relatively small value here. So P can vary from low dimension to high dimension, okay, and the sample size from 500 to 2000, okay. So that here's the truth. You have 10% of the pathways are not broken. So they both have, non-zero values. You have 10% of the, both are 0. So, and 40% of one of them is 0. Okay, so we do this cross validation to select the, the sparsity and do this 200 replicates. So first of all, I show you the result use Groovy solver. This is the commercial solver that you can directly download. And there's an education version that costs very minimum dollars to have in your computer or in your cluster. So here is the case of sample size from 500 to 2000, and P is 100 and 200. You can see that if you increase the sample size, the solution is getting closer. So for example, here I supposed to have 10%, right? So 10% is basically 10, right? And then I should have 40% to 40%. And so you can say that the performance are getting better if you increase sample size. So according to large sample theory, that you can reconstruct this Oracle solution when your sample size goes to infinity. The same situation for this. So that once again, in this solution, you're not only get estimate of your model parameters, but also get estimate of your labels, okay? The eta parameters, right? The labeling parameters. So you can see that they're very satisfactory in the case. So now if you move this, I don't have this result for 50,000. I figure out that maybe, take quite a bit of time to explain it. Like, let me just give you a simple case of 5,000 mediators, okay? So suppose I have 10 mediation pathways. So here I basically have 10 pairs of alpha and beta, both not zero, okay? So that's basically you have unbroken bridge from S to Y via M. So that's the situation I set up as the sparsity. I have, out of the 5,000 mediators, I only have 10 that have this complete bridge from S to Y. So now I have the sample size, okay? So that you can see that the this is the case that you would see that when you increase the red one is the sensitivity, the true positive. So whether or not you are able to identify this 10 sort of mediation pathway. The green ones, the blue ones are the false sort of positive. So you can see that when the sample size becomes larger and larger, you're able to identify, almost perfectly about this 10 pathways, and your false positive are dropping quite nicely. And then you can see that under this situation of 5,000 mediator, that the correlation among the mediators have very minimal effect on the performance of this algorithm. This is the beauty of this sort of the MIO, the integer mixed integer optimization, that does give you quite a bit this sort of robustness on against the correlated mediators. We know that if you do this single univariate screening of mediators, the correlation matters a lot, and you could end up a lot of false positive because of the correlation among the mediators. However, if you do this type of solution based on this simultaneous operation of estimating clustering using MIO solver, then this correlation has very minimal effect on this solution. So what I want to tell you today is that we have tried in the past few years that to develop a new formulation of mixed integer optimization for simultaneous operation of clustering parameter configurations and estimation. And we obtained a very encouraging numerical result where, trying to wrap that for both the numerical part and also the package that we can release to the applied community to use. And of course that the statistical inference is important, but very challenging. And so far we established the selection consistency, and we're trying to see how to use the selection consistency to further establish valid statistical inference with the minimum suffering of the conservativeness. This is the work ongoing. Okay. So we feel that this idea of the mixed integer optimization is the idea of that changing this multi-stage sort of exercise. First do clustering, then do estimation, or first do model selection, then do estimation. So we're trying to say, can we just do this multitask under one operation? So because if you do the multi-stage sort of statistical analysis, there are always a worry of carryover errors. I mean, the carryover errors are largely ignored in statistical analysis, particularly when you consider inference, right? That this carryover error is really something important, but largely ignored in the literature. So doing this one operation, if possible, would help you to mitigate that sort of the carrying over sort of errors. Okay, we found that we feel that this probably is a new direction to really solving all of this sparsity problem rather than doing post-model selection inference, sort of you do model selection first, then do inference. Now, can we do this simultaneously? So, achieve this model variable selection and inference at the same time. So, of course, in the past of 5-6 years, a lot of people involved in the projects in the different stage of their training, where I have colleagues and also students and postdocs that have been working on this project. So that's all I want to say. Thank you very much.
Peter, thank you so much. That was a really wonderful talk. Since we started late, I understand that people might have to cycle off and head to their next meetings or whatever, but we do have time for a couple of questions for Peter. If there's anything specific, please unmute yourself and ask your question. I know there's a bunch of people in the group that do work on structural equation modeling and mediation analysis and so on, so they might have some questions. So please go ahead. Anything for Peter? Peter, what are your computation times like? So when you're doing the MIO, what's happening is P is increasing in computation time.
The computation time is I don't have that slice actually. Yeah. We do have this comparison for the case of 50,000. I think it's roughly for one round is for this Apollo algorithm is I think about 8 minutes or so for 50,000. Okay. Yeah. Okay. So it's not that extremely long, but in that case, Groovy is totally failed, right? Mm-hmm. If you run Groovy and like 500 mediators, it takes forever to get a result that would maybe hours, even days to get a result. But if we run like 5 mediators, use Apollo algorithm, it takes like 1 minute or so. It's very fast.
Okay.
Yeah.
Okay. Anybody else have questions for?
Hi, Peter.
Hi, Len. Nice to see you.
Great talk. Yeah,
you're
nice
not from Bystad, right? You're from
I missed the first few slides, so sorry about that. So I have a question about confounding effect.
Okay.
So I know you mentioned that in your first few slides, and then you talk about the confounding effects. So in your framework, are the confounding effects observed confounding effects, or can you allow for unmeasured confounding effects?
That's a very tough question. This question should be directed down Rubin, not to me. It's really tough question for the whole community. This unobserved confounding is really something very challenging. I think that particularly in the observational study, I don't know if the MIO can be formulated to deal with unobserved confounding. That's something I'm not so sure. I've never thought about this problem. But if you want to use traditional method, right? So this unobserved confounding is basically a very tough question. What I would say that if you have cohort study, right? The study we I've been involved where you have a little bit better sort of attention to the design of data collection, and you work with the scientists, like work this mediation analysis with some of the scientists from nutritional sciences or environmental sciences. They have their substantive science knowledge that can help them to really identify the major sort of confounders. But I cannot say this will be the perfect solution, but at least somehow you use scientific knowledge to identify some major confounding factors. This doesn't mean that I'm saying there are no latent confounding factors. I think that's probably a better solution than a statistical method to solve unobserved confounding. And working with the applied scientists who know the field very well, they know the literature in the field well. But come to the statistical method, maybe factor model could help you to understand some of the unobserved from confounding. So
yeah, I'm curious whether in the mediation analysis literature you have seen instrumental variables. So in structure equations in general, instrumental variables are very popular to do with unmarried confounding, but I'm not familiar with mediation literature.
So certainly that you can do the Medellin randomization, or you use some kind of genomic data to somehow help you to do like Medellin randomization that create the instrument variable, and somehow that can help you postulate the confounding factors. Because here you have, three edges, right? So from exposure to mediator to outcome. It's not as the treatment. When you have treatment to outcome, you only have one edge. Here you have to somehow randomize both exposure and mediators. And when you have high dimension mediator, that this randomization is really something tough to really technically. How do you really handle that? I think probably the people have done a little bit like that in the mediation, the structure equation model mediation analysis. How do you come up with some of the instrumental variables to overcome some of the confounding factors? I'm not aware of a very, very clear or desirable solution at this moment.
Yeah, thank you, Peter.
Peter, there's a question that just popped up in the chat box by Gabriel Odom, who's saying, do you have any published vignettes on how you actually do this in practice? So these complex sort of multiple mediators, how are you communicating them back in practice or applying them in practice?
Yeah, I think this problem actually, was asked by our collaborators, because they are doing this like lipidomics, like they have like 400 lipidomics. They say, of course they could do this univariate sort of structure, even in the univariate case, right? So you still have conservativeness in the actual use of the existing software package based on a bootstrap. So even if you ignore that, then you do this univariate. But when mediators are correlated, you could have a lot of sort of false positive and the worse conclusions. So somehow this problem has been sort of raised by our collaborator. How do you do this as a group, right? So of course now high dimensional as a biostatistician will push the technology a little bit further, like, and sort of the little bit more in advance. But we do actually in our application frequently we need to test a group of mediators to like 5, 10, 15 or something like that. So yeah.
Professor Rao, may I clarify that question a bit?
Sure.
Thank you, Professor Song, for your talk. I was one of the few with some technical difficulties. I joined a little bit late. I guess to clarify my question, I mean, there are places like F1000 or GitHub pages where your collaborators could publish an example data set and then some code that walks through this procedure and shows how to actually apply the techniques that you've developed to answer these real questions. And I was wondering if you had, for instance, a URL or a DOI that I could go and read through how to do
right. Yeah, I think there's a very fair question, and this our responsibility to share some of new technologies that prove to be better than existing one. So we have this first part of my talk is based on this sort of adaptive bootstrap method. That's really something that we want to push out as a package. The paper is under revision for GRCB. It's almost done. If the paper is accepted next year, we will have the package out. I think that would be better than any of the existing packages so far, because you can clearly see that the type 1 error is controlled and the power is better. So that can save a lot of sample size. In the reality, you can find a lot of more signals then. So that's something I am very excited about to push out. For this high dimensional case, so far, we're trying to push this to a low-dimensional Groovy based, because Groovy is a commercial software solver that people can easily download. We did a lot of C++ programming for Apollo algorithm. That could be next, the third stage. But in the second stage, for the second problem, like we could release a package next year, just do this hundreds of mediators. And so that's something we plan to do. We trying to finish a manuscript now. And nowadays, like, we have to protect ourselves a little bit. You don't want to release a lot of details of method before the papers are being reviewed and criticized or by your peer colleagues. And yeah, certainly that's certainly on the list of to-do list that we really want to do it. Yeah.
Thank you very much for that. I will look forward to the manuscript and the package that comes after.